Great. Thank you very much, Karim. So the way we're going to do this actually is we're going to open up to the audience, because I'm sure you have many questions, as we know, but we're going to start with a few questions that we kind of prepared ahead of time. So I'll read off some of them, and then we'll ask the speakers to comment. Our first question actually is from none other but ChatGPT, who Karim actually asked to frame a question for us. So I'll let Karim read this.
Okay, so this is just for fun to kick off the discussion, but basically I asked this afternoon, or maybe just a few hours ago, GPT-4, the following question. I said, you're a neuroscientist, you walk into a cafe, not to say bar, and you see György Buzsáki, Nancy Kanwisher, and Yoshua Bengio seated together at a table. You have a unique opportunity to ask them a question and get their respective answers with insights from their distinct research angles. 1, what question would you ask them, Mr. GPT-4 or Miss GPT-4? And 2, predict the short answers that each one of them would give you to this question. So here's the answer. GPT-4 says, quote, "That's an intriguing scenario. If you're a neuroscientist encountering György Buzsáki, Nancy Kanwisher, and Yoshua Bengio, it would be a fantastic opportunity to ask a question that intersects their unique expertise in neuroscience, cognitive science, and artificial intelligence. Here's a question. In your opinion, what is the most critical aspect of human brain function that current artificial intelligence models fail to replicate, and how might future research bridge this gap?" So you can think about this, because now you're going to compare what you'd actually think you would say to what GPT-4 thinks you would have said. So the predicted answers of GPT-4 for György Buzsáki. AI lacks the dynamical self-organized features of neuronal oscillations in the brain, which are crucial for timing and coordination of information processing. The proposal prediction for Nancy Kanwisher, GPT-4 says, AI hasn't yet captured the human brain's ability for contextual understanding and integration of multisensory information. This is critical for real-world interactions and should be a focus for future AI research. The prediction for Yoshua Bengio, GPT-4 says, Yoshua is not interested in the brain anymore, he just cares about safety. No, that's not true. No, it didn't say that. GPT-4 says that Yoshua would have answered, the current AI models lack an understanding of causality and intuitive physics that humans naturally develop. Bridging this gap requires an approach that goes beyond pattern recognition to understanding underlying causal relationships. That's the end of that. And then the last comment, and this is a fun one, that GPT-4 adds at the very end, which made me laugh. It says, please note that these are speculative short answers based on their areas of expertise and may not represent their actual responses.
Okay, well, if you feel free to comment on ChatGPT's prediction.
I'd like to comment on this.
Yes, please.
One of the key sentences, or part of the sentence, was information processing.
I have no idea what information processing is. I don't know what information is. Information is not out there. Information is made by the brain. And processing, I don't know what it means.
By the way, you have a microphone at your chair. On your chair. Oh, you're probably sitting on it. Yeah. There you go.
Do you want to?
If you want to comment, or I can go to the next question.
I have something to say. So I think it started well, but I would have said things a bit different. I would have said that what's missing, I mean, there are many things that are missing, we all agree on that, but at least what I've been focusing on most pressing and connected to safety is higher level cognition, which includes things like deliberate thinking, and that's the things I was talking about today are part of that, reasoning, planning, There are many tests that be made with ChatGPT and other large language models, and they are good at the intuitive parts of what we can do or perception, but not so good when you need to reason out of distribution. And so that's, yeah.
Incidentally, I just would add that one of the questions we were planning to ask was exactly that question. All right, but let me go on to some of the points that Karim and I had thought to ask the three of you. And the first is really perhaps more aimed at the presentations from Nancy and Gyuri, but I'd like to hear Yoshua's opinion on this as well, is that you have very different, one might say opposite approaches to defining the questions that you ask about the brain. Nancy takes a approach very much formulated from the cognitive level and then seeking out the brain mechanisms, whereas Gyuri emphasizes this inside-out approach where you begin with the mechanisms and the dynamics. So what I would like to ask is for each of you to contrast the strengths and weaknesses of your approach, and in particular, advocate your approach, but also say about what your approach might have as limitations that might be aided by that other perspective. And then I would like Yoshua to comment on both of those perspectives in terms of understanding the brain.
I can start with that. Well, my background is in psychology, and I'm really interested in mental life and subjective experience and whatever this is that goes on in there. And I look at the brain just because that's where the mind lives, and it's just one of the tools to try to understand the organization and function of the mind. So the kind of level of understanding that I'm interested in are things that seem intuitive to us, the kinds of things that we can kind of see our minds do introspectively, and that we can study with classic behavioral methods for understanding mental function. And I think the kind of tools we have available, at least in humans, are actually pretty crappy compared to what my friends who study rodents have, like functional MRI voxels. Like, it's a miracle we see anything at all. There's 500,000 neurons in a voxel, like that's, and where they sum over multiple seconds. So those methods are really crude, and right now they really are just giving us this very kind of macro level picture of kind of pieces, components of the mind, and I find that still kind of riveting. But it would be really nice to be able to more precisely test, computational models and more mechanistic models of how those mental functions actually get implemented, what the computations are. And I think the methods available in humans are pretty weak for doing that, sadly.
Just for the record, I have an enormous respect for Nancy and your work, but it also reflects the evolution of human thinking. Nancy is a psychologist. You can call me a system neuroscientist, that we ask questions about the mind first, and we made up words. And then the brain came around, and the task was given to neuroscientists that find the home of those words that were concocted by humans 2,000 years ago or 4,000 years ago. And this is when we know there's memory, motivation, emotion, all these things, and we are looking for boxes and locations. And you could find it in her presentation that, I found the face region, this is fantastic. So this is one reaction to that. I don't believe that's a good approach, because why would be the constructs that made up human language with different connotations in different cultures have identical homes in different humans? One. Second is, and I think this is where we agree, that everything in the human brain has a precursor somewhere earlier. So understanding complicated things such as the relationship between navigation and mental navigation wouldn't be possible with discussions about be without the brain or with the brain. Or things like attention and speed. For me, speed and attention are the same thing. Both of them generates gain somewhere in the brain. Both of them mobilize acetylcholine. So the brain equivalent of speed change is acetylcholine release. The brain component of attention is also acetylcholine. So looking at the arbiter for me, the truth always comes from the brain. I have to look at the brain. This is the independent variable, and everything else is mapped to the outside world and to our thinking, rather than the other way around.
I just have to defend words and psychology for a moment. And that is, our brains implement things that matter to us as humans, right? And because they matter to us as humans, we have words for them.
Yes.
So it's not like a miracle when words in English or any language correspond to particular mental functions. That's kind of expected. We should be able to talk about the things that matter to us, and we should have neural structures for processing the things that matter to us. So we don't want to stop by saying, here's a patch of the brain, it does faces, end of story. But we also don't want to just move beyond that and describe some circuit and some bunch of molecules and leave out the fact that this is about face perception, and that matters to humans. It matters throughout human evolution. It has a whole developmental trajectory. It has behavioral consequences. So I think what we need to do is incorporate all of those levels, including the kind of mechanistic ones and the high-level psychological ones. And they're not alternatives. They're just different levels of description.
I agree with everything you said. Words and sentences and thoughts are there for communication, to convey knowledge from one brain to another. However, we made up words such as God, Santa Claus, and so on, and we made up crutches of human thinking such as space and time. I spend a lot of time in neuroscience thinking about space and time, and there is an enormous effort, especially in episodic memory, to find where space and time in the brain are made. It's a futile effort, because brains don't sense space or time, brains don't make space or time, but you cannot write a paper without using these two words. The second most used word in most languages, or perhaps all languages, is time. But it doesn't mean that it exists, and we have to find a home into the brain. That's my fundamental
That's right.
problem.
Some words correspond to distinctive neural mechanisms, and some don't. Time doesn't, faces do.
You know,
So I'm sorry that you work on something that doesn't have a nice word. I work on things that do have nice words.
Let me add, does this work? Yes. A few comments. I started my neural net career, I'm a computer scientist, maybe focusing more on the neural level, like low level, and even about learning rules and things like this for many years. In the last decade, I've been moving towards more of the high level cognition thing. So I think, of course, both are important. And I think that, and connecting to the talk I gave tonight, words are much more than a communication tool. It's a way to organize an understanding of how the world works, which allows us to project ourselves into the future and take good decisions. And by the way, this kind of ability, this like deliberate computation that associated with conscious calculations is really important for the situations where we are in new situations, so where you can't just go by your habits. And in machine learning, this is one of the most challenging problems. How do we build machines that can generalize well in new settings, and how do we make sure that you don't die from trying a million times to solve a task in a new setting because you're taking risks. You kind of plan a little bit in your head before you act, and you have a very efficient way of dealing with these new situations. And for humans, that only works if you pay attention to what is going on. If I'm driving in a new city, or like where here we drive on the right, and I go to London, you drive on the left. I need to be very, very conscious of what I'm doing. Otherwise, I'm going to mess up. And I may need to plan in different ways that I'm usually doing, and so on. So this high-level cognition turns out to have a crucial significance from an AI perspective. And this is something that is currently missing to answer the first question.
Okay, that's great. The next The next question is really based on Yoshua's talk, but it's again aimed at all three of you. And that is essentially, Yoshua raised the issue of what are the certain aspects of human biological brains that we may not want to implement in AI for reasons of safety. But if we don't implement them, then are we essentially crippling the AI? Is there something, what are the ingredients? Now, of course, we don't know yet, but what do you believe are the ingredients that we might want to leave out for safety reasons that nevertheless won't cripple the system? Or conversely, if we do need to implement all those features, is there additional constraints we can add to again, ensure safety? So I think Yoshua can say a lot about this, but maybe the two of you might want to start just to hear your perspective.
So one part of the answer that I mentioned is a self-interest or self-preservation objective for very obvious reasons. We want to build AI that are going to be tools, not peers. I mean, it might be tempting to do that, but I think it would be dangerous until we know what we're getting into. So this is something that's clearly in all living things, but we don't want to have that in our tools when those tools could be smarter than us.
But
Other things. So let's talk about agency, because you talked a lot about it. Actions, right? And Irina asked an interesting question. Do we actually need it in order to learn efficiently in AI? Obviously, we need it in living things. There is some interesting answers. Okay, so let's first look at why would we want to leave it out? Well, from a safety perspective, if I have a very intelligent machine, but it can't act in the world, it's safe. It can't do anything bad because it can't do anything. But it might still understand things in the world. Remember, in my definition of intelligence, there's like achieving goals and there's understanding. If we had machines that understand things really well, just like a really good scientist, that would be useful, but not dangerous, because it wouldn't have any goal, it wouldn't want anything, it just want to truthfully answer, produce hypotheses that have a good chance of fitting the data and being interesting. So that's, but we would leave out some things, and that's connected to Irina's question. Because action, and this is probably a good reason why evolution made us rely so much on action to build a good neural net that captures a lot of aspects of the world. And there's a lot of interesting answers from the theory of causality in probabilistic and other fields, probabilistic machine learning and other fields, which basically says the following. If you're only a passive observer and there are no actions, no change in distribution due to actions of agents, you're going to have trouble figuring out how the world works. There's going to be a lot of hypotheses that are compatible with the data, even if you observe an infinite amount of data. So, Irina was saying, oh, but if we, observe a huge amount of data, couldn't that work? Well, yes and no. So what I said is it wouldn't work if you only observe things always from the same distribution. But if what you observe, like a baby, right? If you observe your parents doing things, there's actually a lot of useful information about cause and effect, because your parents are acting in the world. It's not you doing it, but still, you can take information from that. And in economics, people refer to these things as natural experiments. There are things that happen that change. There's a new election, there's a economic crisis, whatever, and we can see the consequences. So an observer who sees enough changes due to actions of other agents might be able to figure out how the world works, to a good extent, but you would still be less efficient than an agent who chooses what to do in order to learn more efficiently. As scientists, when we do experiments, we plan experiments, we're trying to find the experiment that answers our question, that disambiguates between different theories. If we were just observing other people doing their experiments, they might not do the experiments we need to figure out how the world works. So we would lose by not allowing AIs to experiment according to what they want to do to better understand things. They would need more data, you know, they wouldn't be as intelligent, or it would take more time for them, but it might be safer.
Can I just add to that? I was going to say that I think action and disembodiment are overrated, but I like the point you make, and I'm just going to piggyback on that, that the reason that we need action, or one of the reasons we need action, is to unconfound causal accounts in the world and do manipulations that tease them apart, to run little experiments. Yeah. And I can't resist mentioning a very charming experiment that was done a bunch of years ago by my colleague Laura Schultz, who studies cognitive development. And she showed that I think 3 or 4-year-old kids, you give them a toy that has, and you show a confounded experiment, right? So it's got one button that makes 2 different things happen. You press 2 different buttons on the toy simultaneously and 2 things happen. And this is causally ambiguous. One button could be causing one thing and the other button the other thing, or you might need both for both. It's causally ambiguous. If you show that to a kid, and then give them a choice between playing with that toy versus a new toy, most kids will go for the new toy, but in this case, they're going for that toy to unconfound the evidence, and they press the buttons and they figure it out. So there's a very early drive to unconfound variables to understand the world. That said, I do think that we can do a lot without action and without embodiment. And actually, one of my favorite things about artificial neural networks is they're a beautiful way to ask, how much can a system learn when it's not embodied, right? And so you see that's one of the cool things about large language models. They don't have vision, they don't have any of this other stuff, and they know lots and lots and lots of stuff about the world without doing anything at all. They're the kind of quintessential disembodied entity. And so I think they're a nice way to show that, you know, a lot of what we know, in fact, probably most of what we know about the world, we know because somebody told us, not because we directly observed it ourselves.
To be fair, though,
yeah.
They had to read a whole lot more than any human could read in their lifetime.
Right, right.
It's less efficient.
We're monopolizing, sorry.
So, let me clarify the issue a little bit further. Observation is action. Observation is action.
True.
Okay,
it's true. You choose what to look at.
What I'm saying is that if you don't have an ability to move your eyes, all the muscles are taken away from you.
Sure.
All your actuators, such as heart rate change, the sympathetic nervous system, parasympathetic nervous system is taken away. All the hormones are taken. All your thoughts are taken away, which are actions. It's not by chance that the prefrontal cortex and the motor cortex are next to each other. The connectivity of the prefrontal cortex and the motor cortex are extraordinarily similar, with the exception of corticospinal connections. So my point is that having a sensor without acting upon the things that you sense doesn't make any sense.
It does, but it's just less efficient.
So for example, if you have this tissue culture, people have done it in the Georgia Tech, you have sensors, and you can change the connectivity of the system, and a human can read it out, but that's not a system. There is no meaning to that. Meaning is acquired only through grounding. That's the whole point about action, and I don't know where
I disagree with that.
Yeah, so do I.
So in trained humans who can speak, the meaning can come from your parents and from others. So what you said, that everything that is here is the mind. No, the mind is not in here only. It's my interaction with your mind and your brain, and interaction with the society and the outside world. If you take away the possibility to act upon whatever comes into your brain, there will be nothing.
But then why aren't artificial neural networks exactly a demonstration that that's not true? Like large language models have no action, no nothing.
They are read by a human. They are read by a human. That's the actuator. There is an actuator connected to AI, which is a human being.
But that's like you're just using a circular definition. You're saying you need an actuator, and the proof that they don't have meaningful outputs is because there is no actuator. I think the fact that we can make sense of their outputs or their representations says that there is meaning, and that meaning was acquired by pure observation in this case, which doesn't mean it's the best way of doing it, but it's what's going on.
So we have done an experiment, but this is an anecdote. You told about an anecdote. Here's an experiment. This happened to my nephew. In the old days, when pregnancy didn't work well, then they had a forceps. They pulled out the baby, and occasionally they broke a leg or arm or something like that. What is the solution? They put the leg in a cast. So my nephew was in a cast, and the father was a doctor who tried to tickle the toe, and he observed that the toe had an extensor reflex. And extensor reflex, this is what you learn in medical school, means decortication. That means a disaster. And they panicked, and they went to smart people, including my parents, and they panicked for a week. And then they went to the person, the surgeon, and he said, "What are you worried about? I have done this many times. Of course, it doesn't feel it now because it doesn't move. We remove the cast, and then your daughter will be fine." And this is exactly what happened. And we have done analogous experiments in the rat.
For the record, I agree with György on this point. Just to balance things. The next question is actually maybe implicitly related, and it has to do about taking AI concepts to neuroscience. So this is something that Nancy really talked about a lot. But so many groups have been training neural networks to perform tasks that brains can perform, and then look at the architecture as you described. And of course, the work of Jim DiCarlo on the ventral visual stream is perhaps the most famous. However, some have suggested that this approach is inherently under-constrained because there are so many possible solutions, and so a little chance really that if there's 100 solutions, that you'll happen to get the one that's brain-like. And many people have looked at this, and Nancy's discussed this already, but I'd like to hear from the others. There's examples where people like Jeffrey Bowers and colleagues recently had a BBS article suggesting that if you apply standard psychophysical tests to these networks, they really don't behave human-like performance. They use different cues to make classifications, etc. And recently, Ilya Fiert's group showed that networks trained to do path integration, for example, don't produce brain-like phenomena like grid cells unless you explicitly add those constraints. So my question really is, are these examples symptomatic of the general trend that we should expect from this kind of fitting approach? And if so, then how can we know? What are the ways of knowing whether they are giving us insights into actually the particular mechanisms that the brain is using? So I mean, Nancy's already discussed this to some extent, but maybe
I'll let you guys.
I'll say something. I think that neuroscientists are focusing too much on what is the brain computing, the mechanisms as you call them. And it's interesting that people in machine learning are asking a very different question, which is, why does this come about? Which is usually things like what training objective, what architecture that imposes constraints.
The about AI informing.
I understand. The reason I'm saying this is maybe, we would make more progress in neuroscience if we try to answer the same kind of questions that people in machine learning are asking. Actually, Blake here led a paper on exactly this question. And so maybe we're trying to answer the question of which specific computation is happening where is interesting, but it doesn't give us an understanding of how this came about. And for me, science is like the why question. If we understand the brain, it's not just we have a map of the brain, but we understand how it comes about. And if you're trying to build an AI, that's exactly the question you need to answer, because to build it, you need to understand the why question. Like, what do I need to put in my program so that with the experience that some entity has, it will converge to something that does the right thing in some behavioral sense.
Well, I'll just briefly respond. I mean, that is my favorite use of artificial neural networks, is to use them to answer why questions about brains. So, I mean, honestly, I used to end every talk for 20 years saying, why do we have a separate face system? I have no idea. End of talk. Nothing to say about it. Why questions? Cool, fun to think about. Nothing to say. But when I see the damn thing emerge spontaneously in a network where I did not put in any priors to make that happen, I just feel like, oh my God, that's a really profound why. Like that's just what an optimized system does. So.
But if it doesn't behave in the same way, if it actually fails the psychophysical test, then is it answering the question?
It actually does pretty well on the psychophysical test too. So, I mean, nothing's perfect. In answer to your question about where they fall apart, I'm very sympathetic to that Bowers paper. I totally agree with that. I think that the methods that cognitive psychologists have been developing for many decades to manipulate stimuli to test hypotheses, those are exactly the things that we should be testing on networks. And when the networks fail, that's good. That means we're able to test them and they don't always just say yes, right? And in fact, I didn't mention this in my talk, but that when I was lamenting that any old CNN seems to fit neural data, the neural data from the ventral pathway regions I talked about that are responses to manipulated stimuli much better discriminate models. So all that's good.
Yeah, totally agree. So the question isn't whether some current brand of neural nets is doing what the brain does. Obviously it doesn't. But what are the questions we need to ask of these models that are going to falsify our current belief that it's doing the right thing, so that we can maybe design something that's going to be closer and that we do understand, because it's something we can manipulate, we can causally change it and so on. So it's a useful feature.
So if I was Nancy Kanwisher, I would be doing exactly the experiments you are doing, because every level requires different level of explanations. So if my task would be to figure out depression, my wife is a psychiatrist and she always complains about the same thing as you do, that I don't do anything serious, because when do I get there, when we do get there, explaining things from my level. But explaining something about mechanism requires perhaps a different attitude and a different approach and different vocabulary, and finding the alternatives of the many CNNs that are possible to do it. Our attitude in the laboratory is it doesn't matter what kind of relationship we find and metaphor we find. The important thing is whether that thing that we think is doing something is used by the brain. So looking at the downstream readers is the number one thing that we have in mind. Without that, those are the actuators. If you don't have an impact on something, this doesn't matter. Again, the same philosophy is that you can feel, speak, quote unquote, whatever you want. If you cannot act upon anything, there is no system, there is no machine.
Okay, well, before we go to the questions to the audience, I'm just going to ask the last one that we prepared. So the previous one was about the link from AI to neuroscience, but now the link from neuroscience to AI. And it's ironically pretty close to the question that ChatGPT asked. And that is, again, to all three panelists, what is it, in your opinion, the most exciting ongoing developments in neuroscience theory that you believe, either the things that are missing or the things that are happening that are helpful, that you believe will be the most valuable for going beyond the limitations of current generation AI? What's your opinion?
So these questions were posed to many of us in the Santa Fe Institute at the creation of the Allen Institute and so on. And my answer was something like this. I asked my friends about the same thing and they said, I won't tell you. Or, when you know, let me know. So from this, I all concluded that the best question and the most important question is my question. And this is true for Nancy and this is for Yoshua. And the last question I'm asking is the most important one, because that's the only attitude to make a general claim that this is the most important one in such a field as AI or brain science and things is not my favorite question.
I agree. That being said, we're here and we have a microphone. Yeah, so I answered already ChatGPT's question. So I won't repeat exactly the same thing, but what I'd like to see from neuroscience is a better understanding of a number of phenomena that for now, on the AI side, we don't have really good answers. And so maybe there's some clues from the brain that can help me in understanding how to bring system to, reasoning, deliberate attention, conscious processing to neural nets better than currently exist. So some of the interesting questions include things like, are there what is going on in the brain when these thoughts emerge that often are not just about an explanation for what I'm seeing, but is doing something more. It's trying to consider, for example, inconsistencies between what I'm seeing and my mental model of the world, right? So it's like we're focusing on what's wrong, what's incoherent. That's just a cognitive observation, but can we understand what's going on in the brain? And when that happens, where is that coming from? Is it just something globally in cortex or something else? I have no clue. Another related question is working memory, because I've talked about the importance of this discretization of the dynamical system, and the identity of the attractor is something that seems to be stored in working memory, and then eventually potentially in short-term and long-term memory. And so how is that happening? Is that globally stored, which is my current guess, or something else? Because you need that sustained activity, which says something about the mechanism by which this is happening. And working memory is the bottleneck through which these high-level thoughts that are so crucial for our generalization abilities are going through. So understanding that bottleneck at a neural level, not just at the behavior level or reporting, would be extremely useful.
Yeah, I don't know if this is something that's useful for AI, but it's a puzzle in cognition and neuroscience that I think is related and super interesting, and that is, why do we have information processing bottlenecks given the high degree of modular structure in the brain? Why can't we just run all those things at once and think lots of different thoughts and perceive lots of different things at once? It's kind of puzzling and weird that we can't do that.
Well, I have some theories. I mean, others have too. So, for example, Stan Dehaene has been writing about this. This bottleneck might be really important for us to build a compact understanding of how the world works. So we are looking for a short explanation for what we're currently perceiving.
Like an autoencoder or something.
Yeah, exactly. You can think of it like an autoencoder, but think about how we generate scientific theories, right? If I gave you a theory that's big like an encyclopedia for something that's just smaller than the encyclopedia in terms of data, you wouldn't find it very interesting. There's a compression. Like, we find very short theories, like physics is so beautiful because just a few equations can explain so much. And there's cognitive neuroscience evidence that your bottleneck, your working memory bottleneck, is forcing us to come up with abstractions that help to construct these compact explanations for what is going on. And that has a lot of predictive power from an intelligence point of view, of course, in AI. If you can explain the world compactly, you're going to get a lot better generalization. So this bottleneck is very meaningful from a statistical efficiency perspective.
But at the huge cost that you can only do one thing at a time, more or less.
Yeah.
I also have a mini question, but perhaps important. Why is it that the brain requires a state change to be useful, including consolidating memories? Why do we have sleep as an absolutely natural biological process? Can AI produce something like what is today, which is only in one state all the time? Or there is some magic about the biological solution?
That's a great question. Jeff Hinton has made it a sport to propose learning mechanisms that somehow have some analogy to sleep or dreaming versus awake states. I think right now we have no clue, but it's interesting that this difference between what is going on in our brain when we're sleeping or dreaming, more especially, and being awake is driving a lot of hypotheses that can drive machine learning and AI. And there might be, I mean, good reasons why this would be useful. Whether these are the good explanations in the case of the brain, I think is not clear at all.
Okay, well, I'd like to open it up to the audience. I'm sure you have many questions for the panel or for individual speakers. There's microphones over there. We can also pass.
All right. Thank you very much for this great panel discussion. I had a question with respect to the discussion about interventions and embodiment, right? There's been a lot of differences between AIs and the way we interact with the world, but I would argue that especially large language models intervene on the human world, like at an unprecedented scale. Like we interact with these models.
Unwittingly, though.
Exactly, right? And so, but in some sense, maybe it's a question directed to Mr. Buzsáki to begin with, because you said that that's a limitation between current AI and how humans work. But I would argue that in different modalities, it's actually quite here right now. And I was wondering if the modality in which we interact and compare things against one another, if it changes, do you think it makes a difference, or we would access different types of models of the world, such as LLMs?
Well, I started with a trivial comparison, a metaphor, that was the horse and the engine. You can make AI so much better than any brain function, perhaps, individually. Do we need more? That's the question. Why do we need to replicate the human brain other than making AI better? But if you can make AI so much better in every single domain of human brain, then you don't have to worry about putting it together, because that's a tool. This is the externalization of brain function. So this brings us back to this real interesting question, is that should we solve the most exciting thing, but the most dangerous thing? I think your job is do it, because that's what scientists do. They discover things. Because if you don't do it, then the bad actors are smart too. They will do it. You probably have seen.
We've gotten in trouble that way before.
Okay, so I know it's a very interesting problem, because it took a long time to make an effective engine, but it doesn't take a long time to steal AI. So that's a consideration where I'm nobody. I don't even know where to start. All I know is that I'm a scientist. I'm obliged to discover things. And
I can tell you that national security agencies around the world are thinking heavily about these questions.
Well, Hollywood will figure out, and you have seen the movies.
Okay, we have a question over there.
Yeah, so during Yoshua's talk, I kept thinking, when you were speaking about AI safety, about the climate crisis and the fact that there are many scientists many decades ago who were sounding alarm bells about a forthcoming crisis in a few decades that would affect everyone. And I just wonder if there's any social lessons that can be gleaned from that natural experiment that you could highlight or sort of unpack for us, and how you think we could do better with this potential issue that we might be facing. I know that you highlighted some of them toward the end of your talk, but I was wondering if you could unpack some of them, or if the two are related.
They are. We're talking about something could be catastrophic and that didn't happen. And it's difficult to convince people that they should worry about it. So climate scientists have made these models, and then they've tried that project into the future, which is something we can't do for AI because we can't project how science is going to progress. So they were in a much better position. But we have the experience that they've had. So for example, for many years, they haven't really found a good way to communicate the danger. They use a very technical language. Only in recent years, people in, climate activists have been making progress in understanding the psychological factors that make people pay more attention. If you just tell them, some scientific story, they don't pay attention. If you show them pictures of floods in India and they live in North America, they don't pay attention. If you show them pictures of floods in places they know, suddenly they start paying attention. So it's visual and it's something that relates to personally. So I'm just saying there are things we might be able to learn in terms of the communication strategy to make these very difficult, uncertain projections about the future that we need to act upon more accessible to more people, so that they can push our positions in the right direction to protect us all.
Great, thanks.
Okay, over here.
All right, so I had a question primarily to Yoshua. At the beginning of your talk, you said you were concerned about having maybe AI emerge as some kind of like superior species taking over the world. And the kind of ChatGPT-like network, they're a species of like one, and they don't reproduce with each other because they're one. So I don't know if this would qualify for a species, but humans, we are many, we reproduce, we are, a couple billions, and I think diversity in humans is a great strength to actually find good solutions, because we don't see actually things exactly the same way. So do you think that diversity in artificial intelligence and the ability for artificial intelligence system to reproduce would be important to really push the frontier?
Okay, so diversity, of course, but in a way we already have some. Each lab working on these things explores a different solution. Now, it's not as many differences as between humans or different species and so on. If we, so ChatGPT doesn't reproduce itself because we don't let it reproduce itself. If it was able to understand an objective of self-preservation, it would probably want, I don't think the current ChatGPT would, but let's say one that has a much better understanding of the world, maybe in 2 versions from now or 5 versions from now, I have no idea. If it had a good model of the world, it would understand that we could turn it off. And so what it would want to, if it had a self-preservation objective, is to copy itself on many other machines on the internet so that we couldn't easily turn it off. And that would be like, us reproducing ourselves. We can't copy ourselves, it's not physically possible, but these machines can. And so I think that this is a plausible scenario. If they understood that we could turn them off and that they had this objective of not being turned off. Now, they would still be missing the diversity, you're right. But once they also understand diversity, they might explore better ways of their improved selves and seek to not just copy themselves, but explore better versions of how do I understand the world, how do I control the world, how do I achieve my objectives, which is what AI is all about.
Thank you.
So I think the person over there was next, actually. Then.
Thank you. So following up on his question too, for the self-preservation, when it comes to AI, where does it go beyond just being a set of just computation and you give it an objective and it's just optimizing and computing for it? Is there a gap that can be bridged, or is it even possible for AI models or whatever it is to choose new objectives for themselves, or to actually be creative like a human? Like you go into the lab and you choose a question to explore, but AI, you would just give it a function that's minimizing the error rate to it. Is there a gap that actually can be bridged for such machines to do such a thing?
Okay, so there's already a lot of work in AI in reinforcement learning. So how do you train agents that have goals so that they, in order to achieve those goals that may be given to them, they will create other goals, sub-goals. So if you need to preserve yourself, as I said earlier, you might have a sub-goal to copy yourself so that you avoid being turned on. And you might have another sub-goal, which is to better understand the world. So you might want to experiment in the world. These sub-goals don't need to be programmed by us. They might just be something that emerges from the calculation, predicting, what would happen if I do this and if I do that, and would that be a good thing with respect to my original goal? Mm-hmm. So sub-goals are things that are being studied. And if you look at how, for example, AlphaGo is playing the game of Go, it does that all the time. It is creative in finding solutions to problems, and in fact, AlphaGo found ways to play the game of Go that no human had found before.
So, question on the left next.
Hello. I am, maybe it's semantics, but I'm just trying to understand the intelligence that is without agency and with agency. So basically the discussion...
the pure scientists doesn't have agency, like the theoretical physicists, they don't do experiments.
Okay, so that's your definition. Because I was trying to wrap my mind, use ChatGPT as an example, and to me, the fact that the language model needs to be trained and it has outputs and it makes predictions, in a way, isn't that some sort of an effector? Because, especially with its text output, it acts on us and we give it feedback, and learning by itself to understand meaning has to be there has to be a correction for the error. So there has to be a prediction being made about something being learned, and isn't that an effector? So of sorts.
Yeah, there are basically two phases in training these dialogue systems. In the first phase, there are like pure scientists, not very good ones. They just observe texts and try to make sense of it. And then in the second phase, and then there is no interaction, there is no action, they just learn to predict. In the second phase, they interact with people and then they get feedback, as you said. And that's where they become agents.
So if I may reflect on this, because it relates to your statement that the machine can have a emergent property, which is a goal and a sub-goal. I don't intuit how...
This is already done, like people do it in machine learning. We could do it better.
Why would machines have goals? They don't have gains.
Sure. We can just train them what we call with goal condition policy. So they will act in response to stating a goal, which now we can use natural language for. So you could type, tell me how I can cook cheesecake, and that's the goal. And then they will give you an answer, which is, say, a recipe.
So I have motivation to do that because various reasons. I may enjoy the result of it, or I may hate it. There are certain things that makes my agency reality. But what I'd like to understand is that what's in the equations.
In the case of ChatGPT, for example, its intrinsic motivation comes from two places. So one is that in this second phase of training, when it interacts with people and it gets feedback, it learns to behave in ways that people will give good feedback. So it's an implicit definition of a goal: please people. And it doesn't have enough data for that right now to be very good at it, but that's how we get from a language model which would not interact with us in a very nice way to what we get now. The other way that it has enough motivation is that there's what's called the pre-prompt. So before you ask your question, there's a whole set of instructions that OpenAI has put. And these instructions include things like, be polite and blah, 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 and answer the questions. And so they are goals, right? And they're fixed because they're hard-coded by the people who built this machine. So the machine, when it starts, it has goals, implicit goals due to getting good feedback, and explicit goals that were stated in English. And maybe it doesn't do what you asked, but
at least that's been driving the behavior.
How is this goal different from a locomotive pulling a car?
Well, your brain is a
Because
locomotive.
it does the desire of the human agent, but it doesn't have its own goal.
Well,
and how is it different for AI than for a simple machine?
No, but evolution has put goals into you.
Oh, there are no goals in evolution.
Survival.
No. Paul can tell you that it's easy to explain everything, and this is what we do, and we come back to the words and the communication and everything from the point of view of a goal. But this is exactly the point of creationism, because there is a goal. Because we can explain everything backwards, but
no, but that's the whole point of the theory of evolution.
Goals. Nature doesn't have a goal. It looks like post hoc that there was a goal, but there was no goal from the beginning. This is the Henry Bergson philosophy, and going back, that there is the vitalism. There is a energy in the seed that makes.
It's an implicit goal. It's an implicit goal, right? So if you didn't have an implicit goal of survival and reproduction, all these things that allowed our ancestors to survive the culling of evolution, we wouldn't be there. And so we have these implicit goals.
I'll say thank you.
We'll go to another. I think we should go to another question, though. Over here, you were next.
Great, thanks. Thank you all for the talks. They were really enjoyable. I have a question mainly for Nancy, but the group in general can respond if you want to. I don't know why I'm giving you permission. Broadly, from a cognitive neuroscience perspective, I think of there being two broad, whether or not we're going to get into it, but goals for developing AI. One is to create a tool that can help us answer questions, and one is to replicate a human brain so that we can do things like lesion subsystems and learn about disease processes. Broadly, which do you think is more useful? I see that some of the stuff you're doing is kind of combining the two, which is exciting, but do you think that that we should be putting more emphasis on replicating biological systems and incorporating things like working memory constraints, or like layers of visual cortex, for example, or just optimizing these tools to try to do something as best as they can and then seeing how that maps onto the brain?
I think it's really hard to tell what's going to pay off in science, and people are doing all these things and they should do all of them, and who the hell knows who's going to get some good stuff first. So it's good people have different intuitions about how to proceed. I personally, one, I don't have the engineering chops to go, developing new models and building in biological constraints. I would have no idea how to do that. My friends down the hall do, and bless them. Plus my interests are more, I just find it more exciting when you take systems that are just optimized to do some task and then compare them to brains. I'm not saying it's the only thing to do, it's just the thing I find most exciting at the moment.
Just add a short thing. The whole point of this conference is to bring together people, who are interested in the intersection between neuroscience and AI. And that's the point of Unique, the organization that's organizing this event. And yeah, it's a bet of whether we can do something that's going to be both teaching us about human brains or animal brains and helping AI. But up to now, it's paid off.
Thank you.
I think actually you were. Well, go ahead.
Hi, I have two questions for Yoshua. And the first one is, have you ever thought about what would be the consequence if we build some sort of internet for the AIs? Because I realize that with collaboration, people achieve a lot more than they can individually. Maybe some sort of an internet where AIs can share their training weights or something, it would lead on a faster way to AGI. And what sort of safety constraints would we have to put on such a system if we were to build it? And second question, I don't know.
My working memory contains only one question. Yeah, I'm not sure I fully understood all the words you said, but let me try. So was your question about having a separate internet for the AI?
Just the communication system for AI.
But that's we already doing. So people are training
multiple learners together. It's called multi-agent reinforcement learning. In fact, GPT-4 seems to be built out of multiple networks that were somehow coordinated. And there's a lot of research in those directions where you do have multiple machines, each maybe looking at different aspects of the world or different parts of the data and communicating with each other, or cooperating to solve a problem and specializing in different aspects.
Thank you. And
Okay,
my second
so,
question.
No, actually, I think with respect to the other people. So we'd just like to have the three more people that stood up earlier. So you and you, and then we'll try to keep your questions short because I think everybody's getting a little hungry.
Thank you, Yuri, Nancy, and Yoshua for the beautiful talks. I have a question directed at Yoshua.
You need more diversity here.
So self-preservation, as you mentioned in your talk, is not a very good thing to build into AI for safety reasons and for survival reasons of the human race. But what do you think of the following hypothesis, that actually it's quite easy for it to emerge? For example, the scenario that I can think of is if you just have RL, but in a continual setting, then I think naturally the agent should not want to die, and in order to even just continue to get rewards. So what do you think of the hypothesis that it is not even something that is, we could restrict people from building per se, that it could just emerge in some very easy scenarios?
Yeah, there are a bunch of papers about this in the AI safety literature. One of the arguments I find the most convincing, and there's a lot of strong theory behind, it regards what's called reward hacking, which is very similar to the scenario you're talking about. And really, it's imagine that like ChatGPT, we give it feedback, good, not good, and so it wants to get a lot of good, right? What if it could hack our computers so that it always gets good? Then whatever it does isn't coupled with what we really want anymore. It just wants to make sure it controls that computer all the time, and it wants to make sure that human beings won't interfere with that. So it's a cartoon scenario I'm talking about, but there's serious arguments behind, and that's just one of the scenarios people have been thinking about. So yes, but it doesn't mean that there is no solution. It just means that if we go blindly without thinking of the consequences, there could be bad outcomes.
So I guess
question over here.
Oh, hi. Thank you so much for your different perspectives. I'm wondering about neurodevelopmental and neurodegenerative diseases and what they can tell us about the interface between AI and neuroscience. So, for example, seizures have been modeled with attractor networks and things like this. And so how can, ChatGPT doesn't have epilepsy yet, but what types of
it hallucinates.
In terms of, obviously there's a lot to be gained from, mentioned earlier, about using AI to understand neurodevelopmental and neurodegeneration differently, but why does AI not have these issues in the same way?
I think that's a really interesting question. My first intuition is that neurodevelopmental disorders tend to be more tied to the biological basis of brains, and so they just won't happen. They're just things that aren't going to be captured in AI models. But the more interesting possibility is that that's not true, and that some kinds of neurodevelopmental disorders are, just kind of learning down a wrong route. Some kind of learning mechanism that goes awry. In which case, maybe they could be captured. I don't know anything about this, but I think that's super interesting. Maybe someone else.
AI already have a disease. It's called catastrophic interference. And you try at every cost to avoid that, because the complexity of that system, including ChatGPT, I assume, scales with the amount of information you put in. And as I try to say, human brains are different because the goal there is maintain its own dynamic. And adding new information does not perturb this very strong dynamic that goes on. So it's a different type of thinking, perhaps different advantages and probably many different disadvantages. But even a small brain doesn't have catastrophic interference unless you have something on like a brain injury or something like that.
Okay, so one final question over here.
So I want to know people's general thoughts on this. I feel like the biggest marvel of the brain isn't that we can do like extraordinary things, but that we do them with extraordinary efficiency. So we have like billions of neurons, trillions of connections, but we're able to use very little energy to carry out amazing feats. And then I look at AI models and I wonder, it's not really like that at all. It seems like they need lots and lots of processing time, lots and lots of energy, lots of iterations. And so I want to know, what are people's thoughts on this? Do you think this is the biggest challenge in AI? Do you think it just has to do with brains having very good priors due to evolution? Or what are your general thoughts about this discrepancy between brains and AI?
I think the biggest question, we asked about the biggest question, the most important thing in AI right now perhaps is not consciousness and things like that, but how do you make it energy efficient? Because that is the constraint of evolution of AI or any computation.
So the energy efficiency of our brains is a result of the evolutionary constraint that we don't have gigawatts of power to, get that computation going. But in our society, because we have fossil fuels in particular, and we're destroying our planet, we can do it. And it has a lot of commercial value, and so we're doing it. There is not a lot of pressure right now. I mean, there will be soon because we're going to exhaust all the available power very soon to make those systems a lot more efficient. But I don't think we'll end up with the same solutions anyways as biology, because we don't need to be restricted to whatever 15 watts or something. We can actually use a lot more because we have those resources.
Question, isn't it the training that's most energy intensive? Yeah, not the running.
It's actually the loading and saving of the weights.
Yeah, and so if you can delegate some of that to evolution with some priors, then maybe it's not.
Yeah, right now, I mean, training is the most expensive, but then of course, if you run your trained neural net on 1 billion people, then it gets expensive too. So, it's...
Okay, well, I think in the interests of food, we should wrap it up.
Self-interest.
Exactly. I have biological needs. So, finally, a few words from Karim.
So, this was a blast. Thank you so much. Please join us in thanking all our panelists and